Hello and welcome to the Unit 7 Section 2 video on geometric sequences. So in the last section we talked a little bit about exponential functions and how they look and what they do on a graph. Now let's start going into a little bit of application with it. Exponential functions are very much the type of function where applications are used quite a bit, and a lot of it's in the real world. So let's start off by using a real world example and identifying geometric sequences. The NCAA basketball tournament begins with 64 teams after the first 4 games, of course. The single elimination tournament then proceeds until a national champion is crowned. Each round, the number of teams competing is half that of the previous round. The chart below shows how many teams are playing in each round. So in the first round we have 64 teams, and then after that round we go to 32 teams because half of the teams are eliminated. And then another half is eliminated, and we're down to 16 in the third round. And we go from the Sweet 16 to the Elite 8, to the Final 4, and then finally the National Championship game, where you have one winner at the end of that. So all of that information is plotted on this graph. So the graph shows information from the table. If points on the graph were connected, what kind of figure would you have? Well, you'd have a decreasing function. And what type of equation does this represent? Well, judging by the shape, and we know what the shape of exponential functions look like, this appears to be an exponential function. And not only an exponential function, but this one shows exponential decay, as opposed to exponential growth. So the sequence is a geometric sequence because each term in the sequence can be found by multiplying the previous term by a half. The ratio for successive terms, in this case 1/2, is called the common ratio and is symbolized by the variable r. So you may remember back to arithmetic sequences. We had a common difference, and that was represented by d. Now we have a common ratio. Now note that r cannot be 1 because a common ratio of 1 would result in a constant function. So if we multiply the previous term by 1, we just get the previous term again, and that just continues on forever. You just keep getting that same term over and over and over. So here laid out for you is the definition of geometric sequence. And I'll leave that for you to read. In any geometric sequence, the common ratio is found by dividing any term by the previous term. So for example, let's take a look at this. Determine that the sequence is geometric. If so, find the common ratio. Well, we take the term 12 and we divide it by the previous term 8. And that gives us 3/2. If we take 18 and divide it by its previous term, 12, we reduce that. That's 3/2. If you have 27, divide it by the previous term, 18, and reduce that, you have 3/2 again. So it does appear that this sequence is geometric, and that the ratio is 3/2. So the common ratio r is 3/2. Let's take a look at example 2. In example 2, we have 10 divided by 6, the previous term. That reduces down to 5/3. Then we have 15 over 10. That reduces down to 3/2. And already we can tell this is not geometric because these numbers are not the same. Just for completeness, 21 over 15, that reduces down to 7 over 5. So again, this is not geometric. All right, now let's talk about formulas for geometric sequences. So there are two ways to express the geometric sequence. One with the recursive formula, where you're given the value of the first term, and then the second term after that can be determined by taking a sub n equals a sub n minus 1 times r. So remember, in arithmetic sequences, we had plus d on the end. Now here we have times r on the end. Now the recursive formula looks very similar to the recursive formula for arithmetic sequences. And while it is somewhat useful, we're not really going to use it that much. What we will be using more so is the general formula, and that defines the nth term of a sub n, or the general term of the sequence, as a function of n. So here is the general formula. It is expressed as a sub n equals a sub 1 times r to the n minus 1, where a sub 1 is the first term and r is the common ratio. So a formula to find any term of a geometric sequence can be found if you know a sequence, a random term in the common ratio, or two terms. And I'm going to go through how to find any term, the term that's you're asked of, in all three of these. So let's start with a sequence. I think this is the easiest one to do. So if we know that this is a geometric sequence and we want to find the ninth term, first thing we need to find is the common ratio. So to find the common ratio, we are going to take a term, say a sub 2, and divide it by the term before it, a sub 1. A sub 2 here is 10, a sub 1 is negative 5, so our common ratio is negative 2. If you know the common ratio and you know the first term, you can find any term you want, because we're going to take this formula, a sub n equals a sub 1 times r to the n minus 1, and we're going to find a sub 9. Well, we know what a sub 1 is because it's the first term in our sequence. And then we know what r is because we just found that, negative 2. And then n is that term number that we're finding, which is 9 minus 1. And so we've got negative 5 times negative 2 to the 8th. And 2 to the 8th, or negative 2 to the 8th rather, is going to give you positive 256. And you multiply that by negative 5, and a sub 9 is negative 1,280. And that would be your answer for the ninth term. Now let's look at if we know a term and the common ratio. Well, we have the common ratio. That's one of the two things we need, but we also need to know what the first term is. And we can find that by using our general form of a geometric sequence. A sub n equals a sub 1 times r to the n minus 1. We're going to substitute in for a sub n, our term that we're given, 2048 is the value. We're looking for a sub 1. We know r is 2, and since we were given the 12th term, our n is going to be 12. So 2048 equals a sub 1 times 2 to the 11th. 2 to the 11th is 2048. And 2048 divided by itself gives you 1. So our first term happens to be 1. Now we turn back to the same formula, and we are going to put in here a sub 8, which is the term we're looking for. We know what a sub 1 is now. We know r because they gave us that, and we're looking for the 8th term, so that's our n. And so we have 1 times 2 to the 7th, and 2 to the 7th is 128. So our 8th term is 128. All right, when you're given two terms, you need to find a common ratio. To do this, you're going to plug both terms into the general formula. Replacing both a1 with the first term and a sub n with the second term. So let's find the 10th term of this geometric sequence, where a sub 5 is 96 and a sub 7 is 384. So what we're going to do is we're going to set up in our general formula a sub 7 equals a sub 5 times r to the 7 minus 5. All right, when we do that, we know what a sub 7 is. A sub 7 is 384. We know what a sub 5 is, that's 96. And we have r to the second, essentially. So we divide each side by 96, we get 4 equals r squared. And we take the square root of both sides, and you're going to get plus or minus 2 equals r. Okay, it's either going to be plus or minus 2. We don't know which one. But we're going to use both plus or minus 2 to find the first term, okay? So let me show you how to work with plus or minus as we go along. To find the first term, we're kind of back to the same type of problem we had previously, where we're going to substitute in one of these terms. Let's take the first one, and for a sub n, we're looking for a sub 1. R is plus or minus 2, and then n here is 5, and then you have minus 1 on the end. So 96 equals a sub 1 times plus or minus 2 to the 4th. Well, since that's an even power, 2 to the 4th, that's going to give you 16, because 2 times 2 is 4, times 2 is 8, times 2 is 16. But negative 2 to the 4th is also 16, because your power is even. So we have 96 equals a sub 1 times 16. And you divide each side by 16, and you get 6 equals a sub 1. Now let's find the 10th term. Again, we go back to the same formula. A sub n equals a sub 1 times r to the n minus 1. A sub 10 is what we're looking for. We know a sub 1 is 6 now. R, you still have to treat it as plus or minus 2. And then we have 10 to the 10 minus 1 is your exponent. So when we do this, we get 6 times plus or minus 2 to the 9th. Since this is an odd power, you're going to continue to have a plus or minus on here, because positive 2 to the 9th is going to give you 512. Negative 2 to the 9th is going to give you negative 512. So you're still going to have a plus or minus 512 here. And then when you multiply it by 6, you're going to get that a sub 10 is equal to plus or minus 3072. And based off the information we're given here, we're given 2 non-consecutive terms. In fact, there is a term between these two. We don't know if that term between is negative or positive. So the best we can surmise is that a sub 10 is either positive 3072 or negative 3072. We just don't know which one. And that basically wraps up section 2 of unit 7. Just a little bit of a view of geometric sequences, how they work, and how you can find terms in a geometric sequence. So in the next video, we're going to wrap up section unit 7 with section 3, writing and solving exponential functions.